Hello.
Common log.
What's that sound like?
Why is it called common? What do you think? You guys said the base was what? So there's an understood 10, but they don't write it. It's understood. We just see LOG with an X. You just have to know the base is 10. So why is it called common?
The scientific
It's
notation.
not. I don't know if it's the one that's used the most per se. Scientific notation, maybe. What's like our whole number system based on? Doesn't that kind of make sense? Anyway, what's LN again? What's his name? We said it last week.
Oh, natural law.
Natural.
Oh.
But Luca, you're right. What base does he have?
E.
He's a log base E of X. Now we don't actually write log base E ever, but we could if we needed to. If it would help us for solving, we would write log base E. But they write it LN. If you remember why last time, I don't know. Silly way of me remembering it. It starts with an L, so it's a log, right? You could say log natural, but that's weird. Logarithm natural, maybe it's, I don't know. Anyway, so natural logarithm, LN, button in our calculator. Another understood base of E. And just like last section, I said E is going to be a good guy eventually. Maybe you'll have to wait until calculator to see why. LN is a good guy too. He's a whole lot easier to work with than log. Just happens. His derivative formula is way easier. Ask any calculus A, B, or BC kid and be like, hey, would you rather have an LN in a problem or a log? And they'll say LN every time. But let's talk about the ones that have an LOG in them, because those are the ones you guys are most used to. I would say log base B, except the book said log base A, so whatever. But who is A, even though I would call him B? Who's little A? Base. That's why I like calling him B. Just like exponential, I like saying B to the X instead of A to the X. And B for base. And log base B, but whatever. A is a constant, B is a constant, doesn't really matter. X. We're going to call him the argument. He's the argument of the logarithm. So question, if he wasn't there, would this mean much? Bless you, bless you. If that X wasn't there, would that mean much?
No.
It's kind of like me just saying this and saying go, and you're like, there's nothing in it. Exactly! But it's so much harder to see with a logarithm.
Because it's an imaginary text. Very imaginary.
Imaginary. But guys, a logarithm has to have an argument. So if you need to, even though it's not usually written, think about it as log of f of x, log of x, whatever base it is. There is no multiplication. There is no timesing going on right there. It's log of who? Log of x. He needs that guy. Just like we're going to see eventually things like sin. Oh no. Cosine? Just kidding. This is trig, right?
Yeah.
Is this times? Sin times x? Cos times x? Tan times x? It's sine of x. Cosine of x. Tangent of x. If they didn't have it, it'd be like him, remember? Okay. But we're not there yet. No trig this section. And who's y? He's the logarithm. And every logarithm is a power. Logarithms were designed, were invented, were created in order to help us work better with powers. Work better with powers. You'll see that illustrated not on this page, but in some future examples. Logarithms help us break down powers. Now we're going to get back to this in just a moment. It's kind of hard for our brains to think about logarithms, which is why it's common for us to think of logarithms in an exponential form, and that'll be the next page. But first of all, let's just say, hey, you were supposed to evaluate this. How do you do it?
Well, f of x is y.
Because some of you have an updated calculator, and some of you have an updated calculator that has in the math menu this thing called a log base, right? So hold on, go with the log base. Go ahead. The ones with yellow buttons, just hang in there. There's other better ways.
Log base.
Those of you with this, it's not gonna work.
Log.
You can't handle it. But we have other ways. You don't really need it. Neither do they. But log base. Ooh, put a base of 2.
Wait,
Five.
what
Math.
where that at?
Math.
The answer's 5.
Math. Log base is A. There it is. Then plug in 32, and I got an answer of, wait a minute, if it's so nice and pretty, shouldn't there be another way to solve than just with a calculator? It's a 5.
Teach.
2 to the fifth.
Wait, it's coming. Okay, so how about letter C? It must be gross. It's just letter C because it was C in the book. But do another one. What's log base 4 of 2? This must be like a weird decimal, so I'm having you use your calculators, right? There's no other way. That's the only thing to do.
Is it 0.5 or negative? Negative 0.5.
0.5, 1/2. Well, stink. He's not that ugly either. We don't usually use calculators for nice and easy answers like that. So there must be another way. And Sean's like, yes, please. My calculator doesn't do this. So, here we go. How do we convert? How do we think about logs in a different light? Ooh, alliteration. Go English. How do we think about logs in a different light? We basically use this snazzy property of exponential and logarithmic functions. And we might see it again in the future. However, I don't just want to give you a formula and say, here it is. I want to actually show you why it is what it is. So let me show you something spiffy having to do with the inverse nature of exponential functions and logarithmic functions. If I take log base A of A to the x, if I take log base A of base A to the x, wait a minute, base A. You know what that ends up equaling, guys?
X log.
Just x.
Oh yeah, because you can cut them.
It is x log A. But that
That-
cancels. Yeah, they
log
undo
A
each other.
is
Log
one.
base A and A to the x, the logarithm with the base of A and the exponential with the base of A, that all cancels and I reduce to x. They're inverses of it. What? What's going on? Come back. And then if I do A to the power of log base A of x, do you know what happens in that one? You still just get x. They undo each other. Exponential and logarithmic functions undo each other. So a log of an exponential, same base math, just get x, just get the argument. Or I should say just get the power. And then A to the power of log base A, once again, and I just get the argument, I just get the x. So, how can I use that to my advantage? Let's say I have a logarithm, and let's say I'm looking at it, and I'm like, yeah, I have no clue. Like on the last page, log base 2 of 32. Right? How do we undo a log? What you do to one side, you do to the other. Wait, that's weird. She wrote huge A's, and they're like underneath, making this like a power? Why'd she do that? Oh, look, guys. If I do A to the power of log base A, then who do I have left? And what do I have over here?
Whoa.
I'm raising both sides. A to the power of both sides. So A to the power of the left and A to the power of the right. How come? That's how I undo a logarithm. That's how I undo a logarithm. Now, what's so snazzy about that? I can look at a logarithm like an exponential. So, on the page before, without using our calculator, Sean, then here we go. Look at, it's the wrong direction. Oh, it's at the bottom. So if I look at this and I plug in a 32 and I say, psh, calculators, who needs those? Wimps. Anyway, just kidding. They can be helpful in their own good way. But I could look at A a different way. Now I'm rhyming. Log base 2 of 32. Oh. Do you think in logs? I don't think in logs. I mean, I kind of do, but you don't think in logs. So coming back. What's another way of looking at this problem?
2 to the power of y is
You can do a big old 2 and a big old 2 and say, hey, 2 to the power of who is 32? you have memorized the formula, that would have done something equivalent. But what you're technically doing is saying like, hey, let's undo that logarithm with his inverse, the exponential, and we can say, so 32 is equal to 2 to the power of, well, last section, what did you guys do in your homework to solve something like this? You took that 32 and you said, hey, how many 2's are in him? And what would you have gotten? 2 to the y is equal to 2 to the 5, and 2 to the y equals 2 to the 5, y must equal. So what does log base 2 of x when x is 32, or log base 2 of 32 mean? With a base of 2, what power would give 32? The whole logarithm is just talking about a power.
25? Or this 2 to the
2 to the 5th.
oh, that, no.
Los Santos, big 2, little 5. Is that better? So then you guys go ahead and do letter C without a calculator with your hands. You know it's supposed to equal 1/2. Go. Use the same idea. Can you get 1/2 without your calculator? Your calculatrice, your calculadora, that thingamabob. If you're stuck, look at the example. Look at what we did. Look at how we undid the logarithm. My question is, how many of you guys just jumped there and didn't show any work? It's not a bad thing. How many of you guys jumped there? Couple. How many of you guys said, put a big old 4 and say, woohoo? Okay. Either way works. This is you actually showing the steps. This is you seeing the pattern and going for it. Taking the jump was probably what you did last year in Algebra 2. That's okay. Well, now what? Kind of. 4 is the bigger one, right? So how many 2's are in 4? I mean, you can do that, but how many 2's are in 4? Break down the bigger one and say, hey, you're 2 squared, buddy. Now what?
You can break down the other two.
Power to a power is, there's a power to a power, you multiply. Hey look, it's the one-to-one property without having to do some mental gymnastics of like comporting things and trying to figure out what on earth is going on. I can just break down 4, see them as 2 squared, say, oh hey, that's 2 to the 2y. Power to a power, you multiply. Then I say, alright, cool, 2y equals 1, so therefore what does y equal? What did your calculator say? Now technically, you guys saw me do it in the example up above. Who is y? He's, f of x, and f of x was the log. So I go ahead and rewrite it just so you guys realize what we did and what we figured out. But the base of 4 raised to what power is 2? 4 to the 1/2, of course. 4 to the square root. And Luke, the reason why I didn't just take what you said was that 4 to get 2 could have been 4 cut in half, or 4 to the square root, or there's like, I don't know, there's lots of ways of getting there. So I'm going to make sure people knew what I was talking about. So question, even though we used our calculators, did you have to have your calculator on these ones? No, they were nice. They worked out neatly. The second one was a little bit harder, but still not impossible. Let's keep going though. Just in case your mind works this way. Technically there is a formula. A way, maybe I should say formula, we'll say a way. To convert between exponential and logarithmic without using the math and the big awkward numbers that you raise to both sides. That's kind of weird. That you take both sides of? No, that's not true. You could just say, given y equals log base a of x. That is true if and only if a to the power of y is equal to x. Make sure you write things carefully. A is a base, y is a power. You can go back and forth between these two forms. So I have my logarithmic form. And who's this? Exponential form. So I can go back and forth between the two, yeah? I can go from a logarithmic form to an exponential form, or if I don't like the exponential, maybe go back to a logarithmic. And just because this one, for some of you, might be the easiest way of remembering this, I'm going to go ahead and say, hey, yeah, he's kind of important because he comes up quite a few times. But if you understand the math behind it, maybe you don't have to memorize that thing last year. And my silly way of remembering it, I already kind of mentioned it to you, is base of a log is the base of the exponential. Base, he needs a power, go get him. He's on the other side, and then come back for what it equals. That's my silly way of remembering, base to power. Base to the power of the other side equals, come right on back. Okay, now with all that, what if we don't like the log in the base that it's given to us? Sometimes it may not be given to us in the best or the most ideal base that we want. Struggle. And especially if I told you that calculus is so much easier with LNs, you're like, well, stink. Then I don't like log base 2s anymore. Not that you ever did, but you might be trying to prepare and say, well, is there any way to get logs of other bases into LNs or into common logs? Those are the buttons I can hit real fast on my calculator. And poor Sean needs this formula. You can't have that snazzy function. There's something called a change of base formula, and a change of base formula basically says another way of writing y. Another way of writing log base a of x. If either that base is not sufficient or you are being directed or asked to change the base, would be use the change of base formula, which says log base, let's choose another base b of x over log base b of a. Or apply to that whole like, hey, ln ends up being like your best friend, not really, but at least a lot better of a friend than log if anything else. One application of this means you could take ln of x over ln of a, and it should equal the exact same thing. So for you guys to test me out, test this formula out and see if it actually makes sense, we should also be able to find the answers to these two questions by taking ln of 32 over ln of 2 and taking ln of 2 over ln of 4.
What is b though?
Somebody, anything else. So if this is a log base 2, I can make it a log base 13 of 32 equals or over a log base 13 of 2. I can change it to be any base I want, which I think ln is the easiest, plus he's a button you can hit real fast on your calculator. Common log, alright, fine, he's not horrible, but ln's better. So we could have also used common log as well. And if you guys want to test it, plug and chug it. Throw it in your calculator. You don't have to do any simplifying. That was what we did on the last page. But all of these, ln of 32 over ln of 2, log base 13 of 32 over log base 13 of 2, common log of 32 over common log of 2, log base pi of 32 over log base pi of 2. All of those should equal what? Has anybody tested it? Nobody? Okay, just do ln of 32 over ln of 2. Or do common log of 32 over common log of 2. I made them up. Lucas said, who's B? And I said, anybody. That's why I chose 13. Who did ln of 32 over ln of 2? What did it get? 5. Anybody cool with that cool log base? And you're like, I kind of like him? Go do log base 13 of 32 over log base 13 of 2. What'd you get? 5. 2 over log base 42 of 2. Basketball number. 5.
Yeah, it works.
Yeah. Doesn't matter. B is anybody. So I can take a log of any base and I can change it to, and why is that nice for Sean especially? Think he doesn't have a log base button.
You can use a common law.
Exactly. If homework gives him a log base 3 of 13 and there's no nice way to solve it by hand, he can be like, fine, ln of 13 over ln of 3 and I got it, right? Good. Look.
So is the natural number just to give a common base for like two logarithms? But like it's a point there.
For ln has as its base the natural number e. There's a lot of different applications in science and in business especially where growth tends to mimic or to use or to have e as a base. So e happens a lot in nature, kind of like pi, just in different ways. So that's kind of why we talked about ln, because he works with e as well. Did you guys actually try the second one? ln of 2 over ln of 4, log of 2 over log of 4, log base 133 of 2 over log base 133 of 4. What'd you get? 0.5 every time. So you don't have to be able to use a log base button. That's one application. And a second application, you don't have to stay in the log of a certain base, but you do have to use the change of base formula in order to vary from what you've been given. And yes, I'm going to kind of highlight that one as well because he does show up from time to time. And one that you might not think of needing to memorize, but you do. Okay? Okay. Ooh, let's have some more fun. Properties. It's getting us closer to being able to solve some equations, kind of like the one-to-one stuff from exponentially things. And if you guys look, isn't there a one-to-one property of logarithms too? We're gonna like him a lot. Just like we liked that property for exponential functions. First of all, any log, even ln, yes, any log of 1 is 0. How come? Any base to the 0 power is always 1. Second one, log base a of a is always going to be 1 because a to the first power is always himself a. Or I should say a to what power is always himself. That's 1. And as you guys already saw, told you were going to see it again. Log base a of a to the x equals x and a to the power of log base a of x equals x as well. Why? Because they're inverses. This is just stating it nice and pretty. And last but not least, if you have logs with bases matching, their arguments better match as well. Which makes this example down below a whole lot sweeter. A whole lot nicer. A whole lot quicker to solve. Now, if you guys want to see the math of the example down below and not just the property usage. Property usage says, hey, what kind of logs do you have on the left and on the right, guys? There's no number written down. Log the base is 10. It's called the common log. Long story short, are they the same? So, 2 logs, same bases. What has to be true with their arguments according to the one-to-one property? They have to be equal. We can jump there by the one-to-one property. Can I show you the math also as to how this could work? 10 to the power of both sides, what happens? Sweet. That's the math as to why the one-to-one property is what it is. Or at least an illustration, I should say probably. An illustration of why the one-to-one property works. But you don't technically have to show me this math because the one-to-one property says whatever, jump there. And then your little algebraic minds, you have them even if you don't believe it. Some of you are in denial. How do you solve for x? Minus the 3, so you get 5x is equal to 9. Divide both sides by 5 and x is equal to 9. We like fractions, decimals, 1.8. Do we get it? Got it good? Can things get harder? Of course. But are we laying a good foundation? Come on, we got this. Come on, we got this. Let's dig in. Let's show off game time. Well, not quite. That's almost warm up time. Game day. There you go. Every day is game day. Oh no! Wait, how do you solve this one?
If we raise it to the power of 3. Well, I
Oh,
mean,
you
if
can do
we do
that.
like a 3 on both sides and then.
What happens on the left? The 3 to the power of log base 3.
So 2x on 1. And then 1, 2.
3 to the 4th is 81.
Does that make sense?
So then-
Now, some of you might need to do the whole little formula thing. Base to power 3 to the 4th is 2x. You wouldn't have had to show the math. There is that jump you can make. But either way, you got to get here somehow. 3 to the 4th is 81. How come? Because 3 squared is 9, 3 squared is 9, and 9 squared is
81.
Got it. Look at you, mental mathers, didn't even know it. So then you divide both sides by 2, and x is equal to? Nice, decimals. Who wants them? 40.5. Anyway. Okay. So he's a little interesting. There's some extra stuff going on with him. So let's check out number 2.
I mean, you know what's in the first one, so you can just equal to that. Like,
You know what's in there?
you know it's a 3.
Why?
Because, well, it's a 9.
Oh, yeah. If it was a 3, it'd be a 3.
If
Yeah,
it was
you're
a
right.
3, it would be nice.
Don't you have to solve one side first and then side
Or you can do 3 squared. Okay, you can do 9 here and 3
Yeah.
But yeah,
squared.
we did it one side, we have to do the other.
Yeah. But Sean, what should you
That's
ask?
what I'm
You're
saying.
like,
You can do 9 and 3 squared.
Can
So
we solve
with
one
the
side
3,
and
you
side
get rid of
equal to that?
Yeah, can we try to
1.5.
change the basis?
Shh. Don't use your calculator. We don't need it. But thanks. That's where we know we're going. Sean's thinking because Sean has one of these. So he was paying really close attention when I said something. If we don't like or if it's not ideal, the base that we have, what can we do to it?
Oh, sorry.
But what's the only legal way to change a base? Using the change of base formula. And some of you are like, ew, gross, that doesn't help anything. Hold on. Is 9 a power of 3?
Yeah.
Mm-hmm. Isn't 9 3
Ooh, I
squared? Is 27 a power of 3?
Yeah.
Isn't it 3 cubed? Well, wait a minute. I don't know what I'm doing. How? Oh, log base 3 of 3 to the power of. What does this end up becoming? 3 over 2 equals log base 3 of x. Oh, that's impossible. What are we supposed to do now? How do we solve for x? We only have one log left. We only have one log to undo. Can't we do 3 to the power of and 3 to the power of, and we end up with x equals 3 to the 3 over 2?
So much extra stuff. In this
Now.
one.
Plug and chug that to your calculator. Is that a nice and pretty number? Probably not. However, we found it without having to use our calculator. The calculatrice or calculadora, and Karina, yes, 1.5, that's his power. This homework is due on Wednesday. We have some more to do.
Oh.
But your homework tonight is to
Start on it.
Yeah, that's right. They're not hear anybody say no freak out in the hallway.
Did you correct any of the homework? Any of the tests?
We have like people still.
Have you graded it though?
I was just gonna ask, like,
Have you graded
how
it?
have we been doing so far?
Been doing?
Sorry.
Eileen's been grading them. You can come peek after school. I might give you a hint.
You see,
Yeah.
like some people are gonna be
I hope I did.